Okay, guys, let's go over one more example of solving Laplace's equation in spherical coordinates. This is a classic example, and it's one I'm kind of excited to go over because it's related to planetary science. We're always putting conducting bodies, moons usually. They're conducting because they've got liquid under the surface in electric and magnetic fields and seeing what happens. So this is a little oversimplified for what we do, but it's nice to review this because it's related to the math that goes into analytical solutions for what happens to these planetary bodies in external electric fields. So this stuff is used, but again, you guys are getting the most basic version because you're just starting out. Okay, so in this example, like I said, we've got a conductor drawn in red, or kind of like a pinkish color, and it's in a constant electric field. The electric field is in the z direction here, in this case pointing up, and you can see that electric field has polarized the charge on the surface of our conductor, and of course that's polarized it in order to maintain an electric field of 0 within the conductor itself. So all of this charge, this non-uniform surface charge density, is right at the outside of our conducting sphere. All right, so like I said before, we've got an electric field. We've got a constant electric field, which is in our z direction, in the z hat direction. Okay, you can see that the polarization, it complicates the field. The field near the conductor Okay, and notice I'm trying to draw this accurately everywhere where this electric field is making contact with the surface of the conductor. I should have drawn the field lines perfectly perpendicular. I might have not done that exactly right, okay? But just in this problem, just like the other ones, I want to know our potential, which in this case I'm going to assume, again, does not depend on phi everywhere. Okay, if it depended on phi, we'd be in trouble. We couldn't use separation of variables, which is what we're learning about. Okay, so let's define some boundary conditions based on our problem. Okay. Our first boundary condition, we want to recognize that conductors are equipotentials, okay, which means the potential is the same everywhere at the surface and inside our conductor, okay? That is just a result of there being some potential at the surface here. Inside the conductor, the electric field is 0. If you remember, the electric field is the gradient or the rate of change of the potential. So if there is no rate of change, that tells you that the potential has to be 0 inside the conductor. Okay, so our first boundary condition is that the potential for R values less than A, which is the radius of our conductor, they are constant, and we'll call that V naught. Okay, and that's because conductors are equipotentials. All right, there's one boundary condition. Okay, I'm going to get more specific. I'm going to let the potential for this particular problem be 0 at R equals 0, because I can set the potential 0 anywhere I want. Okay, so that gives me that the V naught also has to be equal to 0 because that is definitely inside our conductor. So that tells me that the potential for R equals 0, something more precise, is not just going to be V naught. I'm going to say it's 0, okay? So I'm actually going to scoochie this down. This will really be our first boundary condition. Our second boundary condition, again, will take R out to infinity. And if I get infinitely far away from the conductor in this particular case, or really, really far, okay, Notice that it doesn't necessarily make sense to say that the potential is equal to 0 because I do have a external electric field. So in this case, it makes sense that the potential is going to be equal to the negative gradient, or sorry, the integral of that electric field, such that when I take the gradient of the potential, I do get the negative of the electric field. Okay, so if I take dz of negative E naught z, I do in fact get the negative of the electric field far away from the conductor, which should be constant and in the z direction. Okay, so those are my boundary conditions. Sweet. Okay, I'm gonna start with my general solution, just like we did with our other problems. The general solution for our spherical Laplace equation was, if I sum over L's, it's equal to a to the L, which is a constant, times r to the L, plus b subscript L divided by r to the L plus 1, okay, times p to the L cosine theta, okay, where these are Lagrange polynomials. Having a hard time with that because I've said it wrong for so many years, I think, unless everyone on the internet is also saying it wrong. Okay, and we're going to solve for the potential in the region that R is greater than A. And the reason why I'm doing that is these boundary conditions, they bound the region outside the sphere. Okay, so I'm actually going to specify that here. Sweet. Okay. So that's what I start with, and now I'm going to use those boundary conditions to start solving for some of those constants. Okay, if I go back here and I remember how this coordinate system works, I'm going to draw a little bit on this picture. Well, maybe I'll draw down here. Okay, if my z direction is up, and this is my sphere, then I have, this is maybe a little point on my sphere, and this is the angle theta. Okay, so this tells me that z is equal to r cosine theta, because I want to have this side here, okay, for a particular z value. Okay, so this works, by the way, even if I'm well outside the sphere. Actually, maybe I should have drawn it that way. Let me extend this r to a point outside the sphere. And again, when I'm thinking about this boundary condition, this r is going to be really, really far away, but I can't draw that in this picture. Okay, but either way, the z point, the z value, is going to be the cosine of theta. Okay, so that helps me recast this external electric field in the coordinates that I'm using, in these spherical coordinates that I'm using to solve for the potential. Okay, notice this here, our first polynomial, so for L equals 1. Okay, so now I can rewrite this as negative E naught R times P to the 1 cosine of theta. Okay, so now I know that if I want to rewrite, I now have a boundary condition for my potential, so I know what this is at a particular point. Okay, so I'm going to rewrite that over here. I get negative E naught R times that first polynomial, or the polynomial for L equals 1, not the first one, because the first one is at 0. That has to be equal to the sum over our L values of this guy Okay, as r goes to infinity. Okay, for this boundary condition, I can actually neglect this second term here and rewrite my general solution as something simpler, because that term is going to go to 0. So at r equals infinity, or as r goes to infinity, this term here is going to go to 0. So I'm going to rewrite my general solution without that term, and I'm going to use that to figure out my other constant. So at large r, I can rewrite my general solution again one more time. Without the term with the b coefficient. Okay, so let's look at this guy. I'm going to switch to the next slide. Okay, now we have to remember something about the Legendre polynomials. They are orthogonal, and that basically means you can't build a piece of L out of other piece of L. So I can't sum a bunch of terms here to recreate this polynomial with L equals 1, okay? So that means on our right-hand side, L has to be equal to 1 as well. Okay, the only way I can make these things equal is to say, all right, fine, L has to be equal to 1. That's the easiest way to do it anyways. All right, so if that is true, then I can rewrite this guy like this, and I'm replacing all the L's on the right-hand side with 1. That obviously simplifies things quite a bit. These two are the same polynomials, so they're going to cancel out. The r's are going to cancel out. And I get that our a here is going to be equal to negative e naught. And that is the a at L equals 1, but it's also the a that's in my general solution, okay? So actually, let's just update. We'll say we're updating our general solution. Okay, now the general solution, it's going to look like this. I don't really know enough to say what the b coefficient is. It went away at my first boundary condition just because that whole term got really small. Okay, but I didn't actually define what it was, so I still have potentially this sum here, okay, plus this guy as my second term. Okay, so basically if I go back here to this form of the general solution, if I distribute this sum and this guy, I've got two sums, right? I could sum this term times our Legendre polynomials, and then I could sum over this term times our Legendre polynomials and add them together. Okay, but I already figured out using one of my boundary conditions that for this term here, this part of the sum, L has to be equal to 1. Okay, so now the sum is gone for that term. There is no parentheses here. This is not being summed. L is equal to 1 here, but I am left with potentially a sum right there. Okay, so let's go ahead and apply our other boundary conditions at the surface of the shell to that form of our general solution. Let's see what that gives us, okay? So now we're going to say, oh, this, I don't know what I'm doing. This should be r theta, sorry. Okay, Okay, so now I know at R is equal to A, we've got a potential that is 0. Okay, so let's go ahead and write that out. Lots of sums here. And I'm replacing all of the R's with A's because that's where I'm evaluating the potential for this boundary condition. Okay, so that's what I'm given, and I know this all has to be equal to 0, okay? Okay, so this sum here can only be 0. It can only be 0 if these terms cancel out. Okay, this term by itself will not be 0, and this term by itself will not be 0, okay? So the sum can only be 0 if the terms cancel. Okay, so that tells me that the term on the left side has to be equal to the negative term on the right side. Again, for the same argument, you cannot build potentials out, or you can't build Legendre polynomials like this one, or sorry, this one out of a sum of these Legendre polynomials. This tells me that this can only be possible if L is equal to 1 and if our constant, I should have a 1 there, negative a1 is equal to b1 over a squared. Okay, so this gives that b1 is equal to negative a1 times a squared. Okay, so using both of our boundary conditions gives a specific solution for this particular problem for the potential outside the sphere that looks like negative a1 times a to the third divided by r squared times p, the first, or the Legendre polynomial for L equals 1. I keep trying to call it the first one. Evaluated the cosine of theta. Okay, and I'm just going to write the rest of this. Okay, we can change one more thing. We're going to let what we found before, a1, be equal to negative e naught. Okay, when I do that, then I can simplify this. Move this over here a little bit more. Okay, I'm going to pull out that common polynomial, and that gives me this for the potential outside the sphere, okay? If I write that as two different terms, this is kind of fun. Okay, notice you get negative e naught r cosine theta plus a to the third over r squared e naught cosine theta. Okay, first thing, they both have the same units. That's great. Okay, second thing, notice this is the external potential that we defined. And all we have to do is superimpose on that external potential some induced potential, which is it's induced by the polarization of our conducting sphere. So I think that's pretty cool. Okay, I like it again because you can relate this to a lot of different problems, but you can relate it to planetary science problems. Okay, I'm going to take a little break and then we'll talk about one more aspect of this problem in the next lecture.